Recall that in the last topology video we said that the product topology on the product of two topological spaces, they are Cartesian product, that topology has a subbasis. So today we are going to discuss that subbasis, and in that direction we have this definition. Suppose we do not immediately start with topological spaces. In this definition we have two non-empty sets x and y. Then we are defining two functions. One of them is pi1, it's a name, from the Cartesian product x times y into x, and the definition of pi1 is this: pi1 maps an ordered pair x comma y onto the first coordinate x. And then there is this other function, a similar one but a different one, pi2, which maps x times y into y, and this one maps x comma y onto y, and we call these maps pi1 and pi2 the projections of x times y onto its first and second factors respectively. The first factor is x and the second factor is y, and here the word onto has not really been used carelessly, because these functions really are onto, they are surjective, which you can show pretty easily using the fact that you have non-empty sets x and y. Exactly how pi1 and pi2 are onto, I am leaving that to you. And now using pi1 and pi2 we are going to describe a subbasis for the product topology on x times y, where say x and y are two topological spaces. And this is that description of a subbasis in the form of this theorem, theorem 15.2. Say we have two topological spaces x comma tau 1 and y comma tau 2. Then the following collection is a subbasis for the product topology on x times y. What is this collection? It's a union of two collections of sets, where in this first one we are looking at the inverse images of open sets in x under pi 1. That is, the open sets in x are coming from the topology tau 1, say u. So this first collection consists of the inverse images of u under the first projection map pi 1, and the second collection consists of the inverse images of the open sets in y, that means the elements in tau 2 under the second projection map pi 2. We have to prove that this S is a subbasis for some topology, and that some topology is actually nothing but the product topology on x times y that we already know. The first job in this proof is to show that S is a subbasis for some topology on x times y. And that amounts to showing that if you take the union of all the elements in S, because the elements in S are sets after all, and in fact all of them are subsets of x times y, so the union will be a subset of x times y. We need to show that that union is actually equal to x times y. Is there any doubt about why these are subsets of x times y? Just think of this pi1 inverse of u for a moment. What is u? U is an element in the topology tau 1. That means u is basically a subset of x. Alright. And what type of function is pi1? Pi1 is a function having x times y as its domain, and it maps this Cartesian product into x. So that means because u is a subset of x, pi1 inverse of u by definition of inverse images is a subset of x times y. Alright, so just like that, these sets are also subsets of x times y. That is why if you take the union of all these elements in S, then the union will be a subset of x times y as well. But we do not have to go very far to show that that union is actually equal to x times y. That is because one of these sets is in fact itself x times y, this one. You see that the topology tau 1, because it's a topology on X, must contain X itself as an element in it, because in a topological space the entire set is also open, and that is why pi 1 inverse of X by definition of S belongs to S. But if you go back to the definition of the function pi 1 and calculate this pi 1 inverse of X, you will see that it's nothing but X times Y. That's why S qualifies to be a basis for some topology on X times Y. And now we will prove that that topology is nothing but the product topology. So we write that, so S is a subbasis for some topology on X times Y, which we also name, we give some name to it, say tau prime. And we also give a name to the product topology on X times Y. Let tau be the product topology on X times Y. We now have to prove that these two topologies are the same. To show that tau and tau prime are the same thing, we proceed like this. For any set U in tau 1, that means any open set U in the space X, pi 1 inverse of U is U times Y. Again, how this is equal to this, that I am leaving to you. Okay, it's a very easy thing, you should be able to figure it out. And this is in the topology tau. Why? Do not forget that tau is the product topology on X times Y. And this type of sets are not only in tau, but they are actually basis elements for tau. If you recall the definition of product topology, any basis element in the product topology is the Cartesian product of an open set in X and an open set in Y. One of those open sets is U, which is open in X, and Y is open in Y. So this is the basis element in the product topology, and as such it belongs to the product topology. Just like that, if you choose any set V in tau 2, that means you are choosing an open set V in the space Y. Pi 2 inverse of V turns out to be X times V, and this is also a basis element for the product topology, and as such it belongs to the product topology. In other words, any element in our collection S, that collection is inside the product topology, and that is why S is a subset of the product topology. But if S is a subset of the product topology, then the topology that S generates, that is tau prime, will also be a subset of tau Y. Well, that is because since S is inside tau, so if you choose any finitely many elements from S and consider their intersection, then that will also belong to tau, because tau is closed under the formation of finite intersections, and that's because it's a topology. And then this other fact is also there, that if you consider such finite intersections, any number of them, and then consider their union, because all such finite intersections are in tau, so their union is also in tau, because tau is closed under the formation of arbitrary unions. That's how tau prime is a subset of tau. Why? Because a typical element in tau prime is an arbitrary union of finite intersections of elements in S. That is why. So you have got one containment, and now we are going to prove that the reverse containment is also true. A typical basis element of tau, that means the product topology, is of this form A times B, where A is coming from the topology tau 1 and B is coming from tau 2. And now you concentrate on this calculation. In place of A times B, you can also write A times Y intersection X times B, and that is because this intersection equals A intersection X times Y intersection B, because A is a subset of X. Why is A subset of X? Because A is coming from the topology on X. So A is basically a subset of X. So A intersection X is equal to A, and just like that, because B is a subset of Y intersection B is equal to B. So you get this back. But this is just pi 1 inverse of A and this one is pi 2 inverse of B. So you see that a typical basis element in the product topology is a finite intersection of elements of our collection S. We do not have the collection here, but you know what I am talking about, because these are two elements in S and the number 2 is finite and their intersection is this basis element. That is why by the definition of the topology tau prime, because tau prime is generated by the subbasis S, this A times B will belong to tau prime. But because A times B is any basis element of the topology tau, so that means all the basis elements of tau are elements in tau prime. So their arbitrary unions will also be elements in tau prime, because tau prime being a topology is closed under the formation of arbitrary unions, and those unions are what we have in tau. So that way tau is also contained in tau prime, just like tau prime is contained in tau, and that's how they are equal. And this section ends here itself. There are no exercises at the end of this section. Instead, in the next topology video, we will straight away start the next section, which is about the subspace topology.